Welcome back. In this video, we're going to be talking about phase plane analysis. Many of you will have seen this before in your B44 class back in differential equations. We're going to go into it in a little bit more detail, and I will expect you to be able to do this for a number of different systems. So the setup is pretty similar. So we're going to consider a 2D autonomous system. And it's going to be dx dt is going to be equal to f of x, y, and dy dt is going to be some function g of x, y, where we have all the partial derivatives. So df dx, df dy, dg dx, dg dy are continuous. Okay, so the first thing to note is by the existence uniqueness theorems, only one solution, up to translation, so only one solution passes, I can't spell, passes through each point in space. So we can draw out vector fields. Vector fields in the phase plane. Okay, so let's give us a couple options. Option 1, which is just to draw out vector fields. For every point. Now, this is possible if you have a computer for each point. Now, this is possible if you have a computer, but it's a little bit more difficult if you're going to be doing it by hand. It turns out that although you can do this by computer, sometimes it's useful to do it by hand because with certain types of analysis, you can prove things about global stability of these systems. Option 2, which is what we're going to focus on today, is what's called nullcline analysis. Use nullcline analysis. So let's define this, and then we'll give an example of how this can be applied. So this is definition 5.7 in your textbook. So the x0 nullcline, the x0 isocline, also known as the x nullcline. So an isocline is just a, let me finish defining this first. So this is the set of all points x, y, satisfying f of x, y is equal to 0. And the y0 isocline or the y nullcline is the set of all points that satisfy g of x, y is equal to 0. And so basically what we're doing is we're solving f of xy equals 0 and g of xy is equal to 0 separately. So recall that when they're both equal to 0, you have an equilibrium. And now we're just going to solve each one separately. And it turns out that analysis has some very nice properties. So the x and y nullclines intersect at the equilibriums, because that's obviously where both of them are equal to 0. Also, on an x nullcline, solutions can only move up, down, because in an x nullcline, you know that the x component of the vector field is equal to 0, and so solutions can only move up and down because those are the y components. So up, down, and on a y nullcline, solutions can only move left, right, for much the same reason. Just a quick note on terminology. The reason we call this a zero isocline, so an isocline is a set where f of x, y is equal to some constant c. And the other isoclines are also sometimes useful in graphing these things out, but we're only going to be talking about the zero isoclines, and so those are, because those are so often used in this kind of analysis, they have a special name of nullcline. Just a moment. It looks like my webcam green screen is going all jittery. Oh, there. Okay. Okay, so let's get back. Let's actually see an example of this. Just jump straight into examples since that's a little bit easier to understand what I'm talking about. So this is example 5.13 in Linda Allen's textbook. So we have start out with our two equations, dx dt, and let's say that's equal to xy minus y, which we'll find it useful later to have this in factored form, y times x minus 1, which is some function f of xy. And we have dy dt is equal to 2x minus xy, which is equal to x times 2 minus y, which is equal to some function g of xy. Okay, so what's our x nullcline? Let's do this in blue. So that's when dx dt is equal to 0. So 0 is equal to y times x minus 1, which implies that y is equal to 0 or x is equal to 1. Note that all of this is two different lines. This is all just the nullcline, the x nullcline. So it's just a single thing because it's the set of all those points. And we also have the y nullcline, which is when 0 is equal to x or times 2 minus y, which implies that y is equal to 2 or x is equal to 0. And let's draw this out. So let's see. Actually, let me move this up since we don't need all that space. And let's try to fit all this on a single page. Okay, so we have our x nullcline, which is y equals 0. Well, let's see, this is the x-axis, this is the y-axis. So y is equal to 0. So we have that. And we also have when x is equal to 1. So all of this all of this blue set here is the x nullcline. And then the y nullcline, that's going to be y is equal to 2. Or x is equal to 0. So all of that set is the x nullcline. And one of the things we'll notice is that when the two intersect, you get an equilibrium. So we have our equilibria points here. So equilibria are when they're both equal, when both f of xy and g of xy equal to 0. So this is at the intersection points. And so that is precisely 0, 0, and 1, 2. Note that the point 0, 1, so this here is not an equilibrium because it's not the intersection of the x nullcline and the y nullcline. It's just a point on the x nullcline. So be a little bit careful about that. These are not lines per se. They're sets, and you're looking at the intersection of these sets. Okay. And one of the other fun facts about this, which I am going to ask you to prove in an exercise, so exercise for the viewer, is going to be that the arrow direction along a nullcline varies continuously except at an equilibrium, where it'll change direction if the determinant of the Jacobian at the equilibrium is not equal to 0. What does that mean? Well, we can draw out the vector field, right? So if we have the point here, so let's say we're at the point 1, 1. So if we're at the point 1, 1, where do we go? So if we plug in 1, so let's see, f of 1, 1, well, what's that equal to? F of 1, 1, you plug in that in, that's equal to 0. G of 1, 1 is going to be equal to 1 times, so that's 1, right? So that means that here you're going upward in this vector field because you plugged in f of 0, 0 and g of 1, 1. Or sorry, f of 1, 1, g of 1, 1. What about a couple other points? What about above? So let's say, what about the point here? So that's the point, let's see, that's 1, 3. So f of 1, 3. Well, f of 1, 3, that's equal to 0 again. And this makes sense, right? Because we're on the x nullcline, so the f function has to be equal to 0. dx dt has to be equal to 0. And g of 1, 3, well, that's equal to minus 1. And so that's going down. What about at, let's say, f of 1, negative 1? Again, f of 1, negative 1 has to be equal to 0 because we're on the x nullcline. And minus 1, let's plugging in minus 1 there, that's equal to 3. And so this is also going up. What about at the point 2, 0? So at the point 2, 0, well, that is still on the x nullcline, so that value is still equal to 0. So the x direction value is equal to 0. But g of 2, 0 is equal to 4. So that is still going up because that's the y coordinate. That's going up. And it turns out that if you look here, that's also going up. But if you look at the point, this one point here, so that's what, minus 1, 0. So g of minus 1, 0. Well, f of minus 1, 0 is still equal to 0, but g of minus 1, 0, well, what does that equal to now? G of minus 1, 0, so that's equal to minus 1 times 2, so that's minus 2. So now we're going down. And you can also check that this one also goes down. And so as you see, so as you're moving along one of your nullclines, it only changes arrow direction along one of your, at the equilibria. And it won't always change direction on an equilibrium, but it sometimes will. Let's do the same thing along the y nullclines. Let's look at a couple different points. So let's say we're going to look at f of minus 1, 2. So that's this point up here, minus 1, 2. Well, here the first thing to notice is that the dy dt, so the g function is going to be equal to 0 because you're on the y nullcline. Whereas f of minus 1, 0 is going to be equal to 4. So that is going in the, wait, did I do that right? Minus 1, 2. Oh, I did that wrong. Yep. So minus 1, 2. So that's 2 times minus 1, which is equal to minus 4. So this is going in the left direction. And if we look up here, so that's at 3, 0. So if we look at 3, 0, well, it's still on the y nullcline, so that's going to be equal to 0. But 3, 0 here, well, that's going to be equal to, wait a moment, what did I do wrong? Oh, sorry, 0, 3. Not 3, 0. 0, 3. So that's that point up here. 0, 3, that's going to be equal to minus 3 and 0. So it's going, along the x-axis, it's going in the negative direction. So that's still going this way. And with a little bit of checking, you'll find that it goes this way there, this way here. So it goes in the positive direction there. And over here, it switches direction and again and goes to the right. And so this gives us some sense of where these trajectories go. So it gives you a partial vector field, and you can follow along. So, one of the things that we should have checked actually, which would have made this a lot easier, is if we knew the Jacobian of the equilibria, we would know whether or not it switches direction when you cross it. Here, empirically, we've seen that, oh, well, it does seem to switch direction when you cross the equilibria. And so therefore, the equilibria probably have determinant not equal to 0. Well, they definitely have it, but let's go ahead and verify that. So J of xy, the Jacobian matrix is just going to be y, x minus 1, 2 minus y, and minus x. That's something pretty easy to verify. So J of 0, 0 is going to be equal to 0, minus 1, 2, 0. And J of 1, 2 is going to be equal to 2, 0, 0, minus 1. Let me actually write this out in a little bit more space, since we're going to be doing some additional analysis on this in a moment. So J of 0, 0 is going to be equal to 0, minus 1, 2, 0. J of 1, 2 is going to be equal to 2, 0, 0, minus 1. And so we can explicitly compute the eigenvalues and find the determinants of Euler-Lees. So the determinant here is going to be equal to, well, it's going to be equal to 2. And lambda 1 is going to be equal, lambda 1 and 2 are going to be equal to plus or minus I times the square root of 2. And the trace here is equal to 0. Here, the determinant is equal to minus 2. Trace is equal to 1. And we have two eigenvalues. Lambda 1 is equal to 2, and lambda 2 is equal to minus 1. So we could also compute the eigenvectors. It's pretty easy in this case. 1, 0, and 0, 1. And so one of the things you can do is you can look locally around each of these things and see what's going on. So here, this thing here we think is, if this were linear, this would be a center. We don't necessarily know this for certain. There are other tools we can use to show this, and it does turn out that it is a center in this particular case. And if you draw some trajectories, what you're doing is you'll note that the trajectories have to be tangent to your vector field, and so you end up with things like this. And so on. And one of the things you can do is locally around this equilibrium, so that's this equilibrium down here, we have the unstable manifold and the stable manifold. So this is called the unstable manifold because the eigenvalue is positive, and this is the stable manifold. Note that this is a saddle point, and that's what unstable and stable manifolds are defined for. And so along the x-axis, so in the horizontal direction, things are going out, and in the vertical direction, things are going in. So you end up with things like that. And if you draw a couple more trajectories, you might end up with something like this. And note that the directions, because the directions along, note that when you're crossing the manifold, when you're crossing the isoclines, you have to cross it orthogonally to the isoclines. Or sorry, not orthogonally. You have to cross it either in the up direction or in the left or right direction, depending on if it's the x or y isocline, which allows you to say more things about the function in general. So this is our handwritten drawing based on this isocline analysis of this phase portrait. We can also do this by looking on having a computer draw out the phase portraits and trajectories, and when we do, we'll see that this is actually pretty close. So I took a moment and off camera, I went on Wolfram Alpha and had to draw a stream plot of this particular graph so that you could see the similarities between the two. Actually, let me move myself out of the way so that this comparison is a little bit easier. So as you can see, the stream plot, the trajectories that we drew over here are pretty similar to the ones that you see in the computer-generated version of the stream plot, where you have the center around here, where you're going around in circles, and you have your saddle point over there. But yeah, so that basically ends this lecture on using nullclines to help you draw the phase portraits of nonlinear autonomous systems of ODEs. And this is a combination of using this nullcline analysis along with local stability analysis based on the Jacobian matrices from the linearization of the system around the equilibria. Note that it's important that you have continuous partial derivatives. If you don't, then a lot of what we've talked about falls away. Doesn't quite work out. But in the case where you do have continuous partial derivatives, this is one method that allows you to draw by hand. Oh, sorry, let me erase that. Draw by hand these sort of pictures that otherwise you would need a computer to draw. And so you might be wondering, why should I draw these by hand when I can just use a computer to do it? The answer is very often you will just use a computer to do it, but sometimes it's useful to understand how these things work and also to be able to prove certain types of theorems and do this sort of qualitative analysis without having to go to a computer, or even sometimes doing qualitative analyses that just looking at a screen plot won't give you. So it turns out that you can prove certain things about the directories from the diagram up here that you can't easily prove by just looking at the screen plot on a computer. So that's about it, and I will see you in class.